Move this over here. Good morning, everybody. I hope you are looking at this guy, which is a copy of one of the homework questions from the proportion things. I thought I'd try something a little different. So I'm going to have the questions here, and we're going to go through them by hand. I know that you can use salt, but salt is like magic. You just plug in the numbers and read off the answer. You're not really doing anything. So it's good practice not to use salt when you can and when it's feasible. And there are going to be questions where that doesn't work. So a study was done to determine whether there's a relationship between snoring and the risk of heart disease. Among the 1,105 snorers in the study, 87 had heart disease, while only 28 of the other 1,379 non-snorers had it. So we pretty much got all the data that we need. We're going to calculate a 95% confidence interval on the difference between the two. So P1 will be the snorers, and that's going to come out as, it's in here somewhere, 87 out of 1,105 people. So 87 divided by 1105, and what do they want as accuracy here? 3 decimal places, okay. So 0.079. And the non-snorer people, I'm just going to put you on mute to reduce the background sound. There we go. Oh, come on, Zoom, stop being pain in the butt. Okay, the same guys, the heart disease people we've done, so the other lot. And 28 divided by 1379 comes out as 0.020. So superficially, I think we've got evidence. Would you agree that about almost 8% of snorers have heart issues and only 2% of non-smokers? Now, I don't want you to, I wouldn't anyway leap to conclusions here, even if we do get evidence that people who snore do have a higher rate than people who don't. I'm not going to get too caught up on that yet, because what could be going on here is that snoring is just a strong indicator of heart disease. I don't think snoring probably, maybe it does not. I don't think snoring makes your heart weak. I think snoring might be just an indication, like obesity, and people who are fat tend to snore a lot, that might be the indirect connection. But nonetheless, it's a good indicator if it harms. So we need to find the standard error of those two guys. And that's going to be the square root P1, Q1 over N1, P2, Q2 over N2. And that's going to be 0.079, that's the P1 hat, and 0.921, that's the Q1 hat, over 1105. And I'm going to add to that this fella, which is essentially 0.02, 0.98, and there's 1379 of them. And so the standard, yes.
Oh, never mind.
Yeah.
Never mind.
No, I don't mind people doing that because I do make mistakes. So it's always worth checking. Okay, let's try this horrible calculation. See what we get. Should be able to do it in one go. 0.079 times 0.921 divided by 1105. Then I'm going to add the 0.02 times 0.98 divided by 1379. And the answer I get is 0.009 to 3 decimal places, right? The 8 rounds up. Okay, we've pretty much got all the building blocks. So I'm going to put the package together. I've got my little list here, which I don't screw up here. We're wanting a 95er. And can you remember what the 95% filler should be?
Professor Robertson,
Yes.
the function in between on the square root, is that a minus or a plus in between the two?
Here,
Yes.
it's a plus.
Okay, thank you.
Both are pluses, right? So a 95% confidence interval is going to be that guy, plus or minus a magic z-score times the standard error. Anybody know before I write it down, because I've got it in front of me here, anybody know what the standard error for a 95% is?
1.96.
Well done, yes. So let's see what we got. Oh, I should have calculated that. I guess I'll do it now. The test statistic is the difference between the two, and it's 0.079. Take away 0.02, and I get 0.059. Okay, so 0.059, give or take 1.96 times the standard error, which is that guy. So it's going to be 0.059, give or take 1.96 times 0.009, and the answer I have is 0.018 if you round it off to 3 decimal places, which is what they wanted. And then I'll do a quick add and subtract. If you subtract it, you get 0.041, and if you add it, you get 0.077. So basically, the difference between those two groups is somewhere in the range 4.1 to 7.7%. Okay. So up here, you put the decimal answers. So you would put 0.041, and you put 0.077. If anybody's having trouble with, WebAssign saying it's 4.2 or 0.078, these rounding offs are to 3 decimal places. And I've been rounding off as we go to 3 decimal places. WebAssign might be doing, to 8, 9, because they probably did it in software anyway, so the guy never did it at all. Only rounded off at the end. So if that does happen, shoot me an email and I can fix it, because you are right. I mean, it's just rounding off. Okay, so what we got here is that the difference between snorers and non-snorers heart disease is that snorers have about at least 4% more snorers have heart issues, right? So it is statistically significant. At least we're 95% sure that that's the truth. So on the basis of this confidence interval, can we infer that the population with heart disease differ from the other group? Yes, we can. But which yes do we pick? Yes, because the interval covers 0, or yes, because the interval does not cover 0. So here's our interval. Why did we say yes there? Agreed? I can see mouth moving, so I'm assuming it's that one. If there isn't a 0 in the interval, when they mean it covers the interval, they mean things like this. Do you see 0 is in the middle? It's covered by it. Isn't that bad news for evidence that one's bigger or less than the other. Right. You want the interval to be all pluses or all negatives, because if they're all pluses, it means the first one is definitely bigger than the second. And if they're all negative, it just means the second one's bigger than the first. Both are good, statistically correct assumptions. To me, that is a classic usage of statistics to try and get evidence of something. Now, maybe it's a minor article that you might see in a medical thing, or maybe if you're a nurse, you'll get this little thing and it says, you know, one of the things you might ask your patient is, do they snore a lot? Or do they snore? And if the answer is yes, you might say, maybe you should just check his heart. You know, I'm not saying snoring causes heart disease, but is an indicator that heart disease might be an issue. Not a very strong issue, but it's there. So, okay, here's our next question. In a certain survey, a question asked is whether a respondent favors or opposes capital punishment, right, the death penalty, for people who are convicted of murder. Oh, I'm glad it's not for speeding. Okay. The output for this exercise compares the proportion who said yes way back in 2000, and now they've compared it to those who said yes in 1993. And they're asking to use SALT, but we're not going to. We're going to do it kind of from scratch. In this particular table, quite a lot of the work's been done for us. Let's see, let P1 be the proportion, right? So they're telling me that's P1 and this is P2. So I already know what P1 hat is, they've told me. I already know what P2 hat is, they've told me. I even know, I don't know why they put brackets around it, but I even know what P1 hat, take away P2 hat, it is positive 0, 3, 1. So I got all that for free. Now we're going to find the standard error, and then we're going to do a 90% confidence interval. What I want you to get used to here is the process, because once you get used to the process, it really doesn't matter what the story is, right? Could be a medical story, it could be something to do with business, could come from social sciences. You're still going to do the same statistical process, because what we're dealing here is what the data is telling us. We're not really looking into it any more than that. So it's going to be the big square root guy, P1, Q1 over N1, P hat 2, Q hat 2 over N2. By the way, that's going to be the last time I'm writing this formula down, because there's 2 more questions coming. That formula is there, but hopefully we can see that. Let's see what we get. 0.257. The sample was 2725. Do you see where I got it from the table? 2725. What's Q1 hat? What number is Q1 hat?
Is it 1 minus 2.57?
It is, and that's 0.743. So if you're wondering where the Q comes from, you take it away from 1, right? Take P away from 1. What's left is Q. Now the second guy is this fella. So that's 0.226. And the Q that goes with that one is 774. And that had a sample size of 1488. So here it goes. Square root 0.257 times 0.743 divided by 2725. Add 0.226 times 0.774 divided by 1488, and the answer I get is 0.0. What did they want again? 4 decimal places. Okay, so 0.0137, round up. So there's my calculation. So that would go in here. And they want a 90% confidence interval. When I look at, well, we'll do that in a minute. When I look at this, and especially when I look at the difference, doesn't there look like there's been a change of opinion about the death penalty over that, 7-year time period? In 1993, which is what P2 is representing, it was about 23%. Now it's climbed up to 26%. For whatever reason. So it's going to be a P1 hat, take away a P2 hat. Okay, I got the number in front of us. Does anybody know what the 90% confidence interval is?
0.1 or 1.65.
Okay, that's a good one. You can also use 1.645, depends on what textbook you read. Times this fella, right? So we have 0.031, give or take this guy, times this guy. Let's see what we get here. So 1.65 times 0.0137. And it looks like 0.0226. If I subtract and add, I will get my interval. So 0.031, take away the margin of error, and I get the answer 0.0084. And if I go the other way and add, it looks like I get this guy here, which is very roughly, and I'm just doing it as a rough answer now. It's about 0.8%, and it could be as high as 5.4%. So there looks the statistically significant result here. What that is saying is that we did get an interval that has nothing but positive numbers in it. So doesn't that make P1 bigger than P2?
Mm-hmm.
The interval itself, if I was trying to phrase it, the increase is probably not that big. I mean, 0.8%. It might be, I'll round off. It might be somewhere between 1% and 5%, right? Mm-hmm. So it is an increase, but it's not like twice as many people are in favor of it. Now, that's the kind of information that people in law and social sciences in general like. They like to collect data on people's opinion on everything, and they also like to find out people's opinion as time changes. Society changes all the time. I've got 2 more of these questions, but I don't know. I think I might be beating a dead donkey here. Ever heard that phrase?
Yeah.
Right. I'm a beating a dead donkey here. 1 more. You don't need to see 2 more. I just to show you the difference in the stories.
I think just 1 more.
1 more. I agree. I think so. So we got a choice. So let me give you the choice. In a survey, 95% of the 400 randomly selected married men said that they would marry their spouse again. if they had to do it all over again. In the same survey, 85% of married women said the same thing. So we are going to do an analysis on that to see if there's a difference in men and women. Would they marry their spouse? Or in a survey of college students, 70% of 120 women surveyed said that they believed in love at first sight, whereas only 50% of the men did. So which one of those do you want to see to the end?
Marriage.
Would you marry your wife for love at first sight? Which one do you want to do? Whoever says it first is one I'm doing.
Marriage.
Okay. I wonder if it's that high because they asked the men while the women were watching. Well, I've got to get this joke out of my head. Why do Scottish husbands die before their wives? Say, I don't know. Because they want to. You actually got that joke. Well done. I thought that would be maybe two, whatever. Okay, let's take all this data and see what we've got. We've got a P1 and we've got a P2. So that's men, that's women, right? Self-identified men, self-identified women. 95% of them, okay. So that's 0.95. I don't need to do that calculation. And the other group, it was 85, so I don't need to do that calculation. I can certainly do the, well, that's probably a better way to say it instead of 1 and 2, you know, P men, P women, but too late now. P1, take a B, P2. Okay, there is a 10% difference, right? Good chance that's going to be statistically significant then. Let's calculate the standard error then. Not writing the formula down, just the numbers. Do the guys first. 0.95, the Q gets you 0.05, and in the men there was 400. So it's not that large a sample. On the women's side, it's 0.85, 0.15, and on the men's side, there were 600 of them. Okay, I can handle that. Put all that package together and hopefully we get an answer that isn't wrong. Square root of 0.95 times 0.05 divided by 400, add 0.85 times 0.15 divided by 600. And what kind of accuracy do they want this time? 3 decimal places, okay. So 0.018. Okay, so we've got all the pieces. And what do they want? Oh, they want a 95% against. So the 95% confidence interval is going to be made up of that guy, plus or minus 1.96 standard error. And this difference is 0.10. So I've got 1.96 times 0.018. And I'm looking at 0.036 if you round it off. And that gets me 0.064. And on the other side, it's 0.136. So it's about somewhere in the region 6 to 13%. maybe 14%. So that would be considered a statistically valid conclusion that men would remarry their wife again. And then it just does the, on the basis of this, would you be able to say that? And the answer is yes. And it's yes, because the interval, remember, that does not cover zero thing. That's kind of how they ask it. Do we feel comfortable? I'm not doing any more of these, but do we feel comfortable about the two population 95, 90% confidence interval story and how you read the numbers and how you build all the pieces together? Right. When you do get your test, which is on Monday, some of the questions are going to be in WebAssign and some are not. And this particular question, I will be doing the way we did it in class. So you won't be using SALT. If you're wondering what the heck I'm doing, I'm trying to reassemble my gizmo. So if you hear swearing or anything, try to pretend. What the heck happened here? Ah. You know, there's 4 different ways to put this together, and I've found 2 of the wrong ones. Oh, watch. I don't know if you can see this. You see my little dog? He's having a snooze. You know when somebody says that phrase, it's a dog's life? I'm not sure where the heck I'm now. Okay, we're getting there. I don't think it's accurate. Oh, well, at least our dogs, they have a great life. I mean, it doesn't work. I pay for all his medical, right? He doesn't have house chores, right? And we love him to death. I mean, that's a pretty good job, isn't it? I think. A wee bit ready, maybe touch lower, straighten up, touch, I don't know where I am. Something's not right. Right, well, after that little interlude, what's missing? There. Gotcha. Okay, we're moving on to our next section. We just finished essentially doing sample proportions, right? And we did it with one sample, and we did it with one sample proportions, we did it with 2 sample proportions. So now we're going to look at means. And today we're just going to look at one sampling distribution. And we're going to kind of figure out how do we create confidence intervals when you're talking about a sample mean rather than a sample proportion, right? So basically, sample proportions are only going to get used in those questions, you know, the ones that talk about, do you like Pepsi or Coke? You know, it has to be a question where there's a yes, no choice. In these questions, you ask people their height or their weight, right? And so what you do here is you kind of average it out and you do a mean. So imagine that I collected a sample of 100 Scottish people. And I found out that their mean age was 41. And this is a random sample of 100 Scottish people. And I would like to create from this storyline a confidence interval. Let's say I want to find a 95% confidence interval. This is going to be more difficult than you think. The 90 or 95 in this case confidence interval has a formula. That's probably the easy part. It's going to be X bar plus or minus, and it's going to be a magic t-square, and then it's going to be the standard error of X bar. And there's a formula for the standard error. And it's the square root of S over N. Oh, so this 100 people, I found their standard deviation, right? And their standard deviation was, say, 5. Now, I know this guy, so that's easy. I know this guy, or at least I will in a minute. I think I'll do it over here. No, I can squeeze in here. I'm doing right. The standard error of the mean is the square root of S, which is 5, divided by this guy. So the standard error in this particular question is square root of 5 divided by 100, and the answer I got is about 0.22 and some other digits. I'm doing 2 decimal places. So we are looking good up to this point. So you might be thinking, where's, what's the problem? Well, this guy that I haven't written the value down to, you might think he's just 1.96. And he would be if he was the magic z-square. But it was discovered, I think actually it was discovered by an Englishman, that you don't get accurate results when you collect the mean of a sample. Because some samples are big and some samples are small. And this piece of the formula helps with that, but it doesn't totally help with it. What was discovered was that this magic number is heavily dependent on the sample size. So this 95% special value, the special t-square, changes when the sample's 100, and it's especially important when the samples are really small. Side issue, but I'll tell you right now, it's kind of interesting. I believe, this is what I read anyway, that this is called the student t distribution, if you're interested in the jargon of it. This guy worked for the Guinness Company, true story. And he worked in their quality control, and he discovered that the normal statistics was not coming up with good answers, right? It predicted one thing, but reality was contradicting it more times than it agreed with it. And that's always a good sign in statistics that maybe you haven't done the job right. And so he worked on it, and he discovered and created this new distribution where you change the t number depending on the size of the sample. And he did it, I'm sure, through experiments, right? He did tiny samples of only 5 things, but he did it lots and lots and lots and lots of time until he figured out what the magic t-score that was reality was. But he never published it under his own name, which honestly, for the life of me, I can't remember what it is. He published it under the name Student. He was called Student, like Joe Student. And the company that he worked for didn't want him to publicize anything. You know, the kind of thing, if you work for a pharmaceutical company, they don't want you to tell anybody anything because information is money, right? If you figured out a better way of doing stuff, you don't want to share it. But anyway, he had the bigger cause and he shared it. So that's why we know about it, which is kind of cool. So what is this guy? Well, it depends on your sample size. So here's our first little problem. How to find the magic t-score? Because once we know what it is, the rest of the calculation is easy, right? The hard part is just going to find this guy. Now, first you find what are called the degrees of freedom. That's the name they give to this thing. And the degrees of freedom is just n minus 1. So in this case, it's 100, take away 1. The degrees of freedom are 99. Second thing you do is you look up a table and you go along the row with 99 till you find your magic t. Now, if that wasn't too messy, it does get messier. Darn it, I'm going to have to close the screen for a second. I'm hitting buttons here and I don't know what I'm doing. I want you to go away. Oh, there we go. Right. Right, let's see where we are here. I've got this fella here. I'm going to move him over here. I just printed this guy, or at least I just turned it into a PDF. I'll be putting this guy in Canvas so you can get a good copy of him. Let me show you the guy I'm talking about. Now you have to do a tweak to it. So here goes. Degrees of freedom. You see them coming down here? Now, do you notice that the degrees of freedom, right? And then along the top there, you have the confidence level. So what were we doing there? We were going to do a 95, weren't we? So that would be here. And then if it was a perfect world, wouldn't I read down here until I got to 99 degrees of freedom? Did you see that? But I don't have a 99 because this table doesn't do every number. So here's your first decision. Do I use 90 or do I use the magic number for 100? What do you do if there's 99 degrees of freedom? Which one do I use?
100?
Yes. And if it's 93 degrees of freedom, you still use 100. And if it's 91 degrees of freedom, right? So you can decide on your rule, but be consistent with your rule, right? So in this case, we are going to go for 1.98. While we've got this table opened up, suppose my sample size is only 10 people, right? Could happen. And I wanted a 99% confidence interval. Can you see that my magic number, God, my eyesight's not great. There it is, it's here. Wouldn't the magic number be 3.17? If I had 1,000 degrees of freedom, and I wanted a 95%, can you see the answer is 1.96? Now, if it was an infinite number, do you see that you get the magic z-score? So when your data is huge, basically over 1,000, your magic t-score is just a normal z-score for 95. So it's a hiccup that for some reason causes more trouble than it's worth to some students, hopefully not you. And now I have to figure out how come I can't close yous off. I'm in trouble. I can't find, oh, there it is. It's hiding under a window. Gotcha. Phew, that was dangerous. Right. No. 1.98, wasn't it 1.98? I almost forgot her answer. Thank goodness. Phew. So I'm going to return back to this fella. And it's going to simply just be 41 plus or minus 1.98, 0.22. And if I'd thought better, I would have given myself more room, but never mind. 1.98 times 0.22. And the answer that we got here is 41, give or take 0.44. So as an interval, 40.56 and 41.44. So what we could assume from this analysis is that the average age of Scots people is somewhere in the range of 40.5 to 41.5. So we now have a 95% confident that we know the average age of all Scotsmen. And we did that with a relatively small sample size. Do you like the strategy? The T thing's a bit messy, but you know, you can live with that. Okay, let's suppose we've got time. No, we don't have time. Okay, if I started one, I wouldn't finish it. So you lot can say hi right now. And while you're saying